I wanted to ask you about your research that you're finding with the changes that we're seeing in upper elevations with fire activity in the mountains.
Yeah. So most of my research is focused kind of on the weather that wildfires produce, the kind of extremes that can come along with these large fires. And sometimes here in the forests of the Sierra Nevada, we see these particularly large fires. We're seeing that this year with the Dixie Fire, the Tamarack Fire, and earlier with the Beckworth Complex and the Sugar Fire, all of which are producing pyrocumulonimbus clouds that generate lightning. Some have produced very strong vortices and whirls capable of damage, and other strong winds. And so we're really seeing those profound impacts from the fires manifest in the weather.
I think more than ever now we're getting the video. So it's really surprising to everybody to see how erratic it can be. But this is not anything new, right?
Yeah, I think that's a great point. And firefighters have been living this reality for decades, and have shared their anecdotes. But now we have social media to see all these different vantage points. But to be honest, it's actually very useful scientifically. We're able to take observations that both firefighters and the public are making, go back and try to understand what exactly is going on in these environments. And it turns out a lot of the things that have been described are what they seem. They're tornado strength vortices, sometimes true fire generated tornadoes in some of these environments. And we're starting to get our finger on the pulse of what's going on from a scientific perspective to go along with the firefighters' experience over the years.
I wanted to ask you too, like, what's the difference between like a fire whirl or a fire tornado? What's the difference between those?
Yeah, this is a very common question, and really a lot of these events, they're kind of on a spectrum or continuum. But the fire whirls tend to be transient, small features, so they're short duration, a few tens of meters in scale. So maybe like 100 meter or 100 feet across. When we're talking about fire tornadoes, we're talking about things that extend 10, 15,000 feet into the atmosphere, are often connected to an overlying fire generated thunderstorm, and are going to have winds up around 100 miles an hour, perhaps more. For example, in the Kari Fire, we saw winds of around 140 miles an hour. So these are winds that are capable of doing tremendous damage on their own right. And then you add into that the combustion of the fire, and we're talking about really deadly situations.
That's pretty unbelievable too, when you see the video and just see how powerful it is. And to think that that's what fire crews are up against when they're trying to battle the fire.
Yeah, and that's really one of the difficult things with these extremes of fire behavior that we're seeing, is that you really can't battle them. It's get crews out of the way at that point, and direct attack on the fire is no longer a manageable situation. And so that doesn't help anybody. We got to get people to safety. But yeah, you can't contain a fire that is, behaving in this way. And so it's kind of scary to think that, we're only just, we're not even through July yet this year, and we're seeing these extremes already that we might typically associate coming along later in the season as we get into late August.
And are we seeing more fires, or is this something that has been happening in history, but we just didn't have it documented?
I think it's a little bit of a mixed bag, but we're certainly seeing more extreme fire and more big fires. So when fires are burning, they're burning hotter. Those one-day huge runs that the fire are making do appear to be bigger than they have been historically. Total acreage, there's not always, historically California has burned a lot, but it's kind of the nature of the burning that's really changing. And kind of fingers crossed we don't go as extreme as we went last year. But again, we have a long way to go in this fire season, and I feel like the fatigue is already setting in, and it's going to be a long haul this year.
And what do you think is contributing to all of this activity?
Yeah, again, fire is very complicated. It's kind of at the nexus of forest management, human development, and climate change. And but it is important to talk about the climate change piece. We know it's getting warmer. It's getting considerably warmer and consistently warmer, and that affects the fuels, which really integrate the weather conditions. So that's kind of this moving background, and then you get years like we've been having, where we get drought and things dry out very early, like we've done this year, and that kind of sets the stage for these explosive fires. but yeah, that shifting baseline, a warming climate, is really an underpinning to all of this, the backdrop for it.
And I guess it's also, the problems that we've seen with more lightning activity, as well as more of the fires that are started by transmission lines and, man-made causes.
Yeah, exactly. Most of California's fires are human caused, but as we've seen, we can get fires from these lightning strikes. Last year we had our major lightning outbreak. Some of these big fires this year have been lightning started fires, like the Tamarack fire and the Beckworth complex. So yeah, again, the common denominator is kind of the fuels. We're going to get ignitions one way or another. It's either going to be lightning, or it's going to be human sources or transmission lines. And then, the fuels are ripe for these explosive fires, and you get the right weather conditions setting up too. And then we get things like these cumulonimbus, these fire generated thunderstorms, like we saw in the Dixie fire just a few days ago, with these kind of spectacular images. So yeah, it's all those ingredients coming together.
And so we were doing the story this morning that they're kind of choked in with all of the smoke right now in New York City and New Jersey. And so a lot of people may be wondering, what's in all of this ash and the smoke that we're seeing?
Yeah, that's a great question. And we have some kind of pilot research going on right now to look particularly at that ash part, the stuff that's falling out of the sky, because that's what we can see with weather radars. But you're right, smoke is becoming one of the major export products of the Western United States. And there's a lot of what we call PM 2.5, very small particulate matter in that smoke, especially the stuff that goes long range. And that is very unhealthy to breathe. Fortunately, a lot of the smoke that goes east from here is up above the surface. But as we know, with the lightning outbreak last year in the Bay Area just being completely inundated with smoke, when that stuff gets close to the surface, it's very unhealthy to breathe. It eludes our filtration, and it's linked to all sorts of negative health impacts for humans. So really not something we want to be breathing. Of course, we all have good N95 masks now, so those do help with smoke. So perhaps we'll be using those more as the summer goes along here.
And so how much of that does a mask, or I guess most people do have cloth masks or the surgical mask, do those even help with some of that particulate matter?
I'm sure they help a little bit, but really it's those N95 masks that this stuff is very, very small. And that's the problem with it is, it eludes our natural filtration systems in our nose and our mouth. And so having a mask that's specifically designed to filter out particles of that size is really what you want. So those N95 masks are really the right tool for the job when it comes to smoke.
And give me an idea of like the scale of the size of what we're seeing in that ash, like compared to a piece of hair.
Yeah, great question. So we have a huge range of things. So the really fine particulates, the smoke particles are microscopic. We can't see them by eye. They're much smaller than the cross section of a human hair. So you could fit many, many, many of these particles into a human hair cross section. In contrast, the ash particles that you might actually see raining down on your car and accumulating on the surface, these are more like snowflake sized things, which have scales. I do everything in metric units, but in millimeters to centimeters, so less than an inch typically. But we can see these flakes falling down, and those aren't as much of a problem from a respiration standpoint for us. But at the big end, we can see big pieces of bark and debris lofted into these plumes, and that stuff is a problem because it can still be on fire. And of course, if it falls back to the surface and it's still on fire, it can cause those spot fires, which are a major mechanism for moving these fires through the landscape. So we're really trying to understand that whole mix of what goes up into these plumes, what comes back down to the surface, and how it affects both human health and fire spread.
And so I remember last year during, all of the fires that we had, and we were just socked in with smoke for like at least a month. And at some point, like my kids were just going crazy in the house. So we go outside just for small, short periods of time. Like, how does that affect your health, even just breathing it in for 5 minutes?
Yeah, that's a good question, and maybe one that I'm not going to have the best scientific answer for. I think maybe a good context is thinking about the micrograms per cubic meter in there. So at the worst, we were probably seeing things around 100 to 150 micrograms per cubic meter of this PM 2.5, perhaps a few places worse than that. A cigarette, if you were to just directly inhale smoke from a cigarette, is probably 600 to 800 micrograms per cubic meter or something like that, I believe. And so, it's, you wouldn't want your kids out there smoking cigarettes, hopefully. And so it's the same sort of scope of the impact of that. But at the same time, it's not an immediate kind of threat to you unless you're in those hazardous groups. And obviously a lot of us are, where these can, the smoke particles can exacerbate underlying health conditions. We see upticks in emergency room visits for asthma and other respiratory stuff. But some of the longer term stuff is more actually cardiovascular. It can affect your veins and stuff. So it's really not something that you want prolonged exposure to. I don't, or really any exposure to, but obviously we all have to stay sane too and get outside.
And so I know you've been also looking at how the ash that we detect on radar, how that travels. How far can some of that ash move, and how are you able to detect it on the radar?
Yeah, that's a great question. So the weather radars see these plumes coming off of the fires by bouncing some of their energy off of these ash particles, and then that comes back to the radar receiver. And we can actually see some of that extending about 100 kilometers downwind from fires. So, for example, I live in Truckee, California, and last year during the lightning fires, I actually was collecting ash falling here from fires in the Bay Area. So it can travel quite a distance downwind. The large material, the stuff that is concerning for spot fires, tends to only travel a few kilometers or maybe even 10 kilometers and could be starting spot fires in that range.
And so, as far as climate change and how this has affected, the activity that we've seen, especially in the upper elevations, I'm guessing maybe because it's warmer and drier up there than it used to be. What are the impacts that climate change is having on fire behavior?
Yeah, well, again, bigger, more intense fires is the key thing that we're seeing. We're also seeing that lengthening of the fire season, and all of this gives us more opportunity for extreme fire behavior. And one of the things that I think a number of researchers are looking at is what kind of forest comes back after a big burn, too. It's not necessarily going to be the same forest that was there before. It's going to be a forest where the species are kind of more adapted to a slightly warmer baseline. And the big thing is, as it gets warmer, it draws more moisture out of the soil and out of the vegetation. The atmosphere gets thirstier basically for moisture. And so it's not just the heat, but the demand for water that the atmosphere has that we see impacting the fuels, the way forests are going to come back, and then ultimately also the fire behavior that we're experiencing. And this is a good example of upper elevation forests this year may be particularly prone because it's also kind of mapping onto a very low snowpack season. So we dried out very early up here, and we're seeing big fires much earlier than we normally would.
And so, what's some other things that your research has found that's pretty interesting that you'd like for people to know?
Yeah, well, the big one is these fire generated tornadoes right now is really the focus of a lot of our research, and trying to understand which fires do and which fires don't produce these really scary tornado strength vortices. And what we're finding is that there are really some common signatures in the fires that do. They get big enough that they block the airflow and start acting like almost like a rock in a river. They split the incoming winds around the edge of the fire, and those winds wrap around the backside of the fire. And we're starting to see that there's a radar signature with that, where we can see that happening. And sometimes that's kind of an early warning sign for when a fire might be getting to the point that it can produce these sort of tornado strength whirls. So that's really the focus right now, is trying to understand that. And then hopefully, if we can understand it, be able to issue early warnings and watches when fires start towing that line where they might get to that point.
Is that something like a signature you see with like gate to gate shear or something like that, or does it look different?
Yeah, that's exactly it. It's the gate to gate shear. So how strong the inbound winds are next to the outbound winds in the radar. And we see this pocket of air behind the fire start going in the other direction. And that sets up for these shears on either side of the fire. And those are kind of the birth regions or the genesis regions for where we're going to see these vortices emerge. We've seen that they can have strengths of equivalent to EF2, perhaps even EF3 strength tornadoes. So really scary stuff.
And how do you know which direction it will travel when it starts to develop like that?
That's a great question.
Because it's not from like a low pressure where you expect it to go off to the east. It's
yeah. And I think we're starting to get some evidence for that. We're seeing two modes. One is what we would call a embedded or anchored vortex that is going to stay connected right to the edge of the fire, right on the edge of the head fire. And so that's actually not going to travel very much. It's going to move kind of along with the fire. But there's another kind of flavor of this that we call a shedding vortex. And that's actually going to move downstream along these shear zones. And we've seen that it propagates right along that shear zone. So we actually can, from the radar, have some sense for the area prone to be exposed to those winds. And again, this is all kind of preliminary work, but I think that the ingredients are there to really start shedding some light on what's going on. And from a scientific standpoint, that's kind of exciting for us to actually have something to latch onto, as opposed to just be in the dark on these events.
And tell us about like your group that goes out to do the research. Like, how many in your team, and what are you all researching right now?
Yeah, so I have a group of grad students up here at the University of Nevada, Reno, and most of our work right now is actually on using these operational weather radars. So the same radars that we're using to track, winter storms coming into the region, and taking data from those on large events and looking for these signatures. We also have some collaborative efforts with colleagues at San Jose State University, in particular, where we go out to larger incidents with deployable resources like scanning laser devices that we call LIDARs and scanning radars like they have at San Jose State, both to prescribed fire and to wildfire, and trying to look for these sort of plume dynamics and wind flow dynamics on these events. So there'll be more of that in the future, trying to get that really fine scale information that we can only get with research instruments, in addition to kind of the information we get from our baseline instruments, these weather radars that are out there operational every day.
Right. All right. Anything else that you'd like to add?
No, I think that's it. Okay.
And where can I find like some of your research and all that stuff? I know you post a lot on Twitter.
Yeah, exactly. Yeah, Twitter is the science blog of sorts these days. So I'm trying to think what a good resource. Google Scholar is kind of the landing page for me when I look for where the publications are detailing this stuff. And we have a publication that we're hoping to get out this summer about these radar signatures of these vortices. So look for that in the future. We also have a new app through Citizen Science Tahoe, which is a citizen science program designed to look at these ash particles falling out, where there's an interface where people can use their smartphones to take pictures of where the ash is falling and how big it is. So that's also run by DRI, the Desert Research Institute up here at the University of Nevada, Reno.